We are on the verge of something absolutely fascinating in the world of computational neuroscience. Welcome to This Explainer. Today, we're asking a huge question. What if analyzing resting state EEG could completely change how we understand neurodegenerative disorders like Alzheimer's and frontotemporal dementia? We are unpacking a brand new perspective called the Ecepj model V2.0.
Okay, let's dive right into this. What if the way we've been looking at the brain's electrical activity for decades has been missing a crucial piece of the puzzle? Imagine trying to read a crisp digital signal using a clunky old analog receiver. That's exactly the core question driving the incredible research we're breaking down today. Here's our roadmap for today. We're going to start with brain signals and dementia, move into rethinking continuous brainwaves, and then introduce the neurobyte framework. After that, we'll look at building a standardized pipeline, explore the fragmentation hypothesis, and wrap up with the future of biomarkers. All right, let's jump right into section 1, brain signals and dementia, and look at the human stakes. So doctors and researchers, they've known for a really long time that resting state EEG activity changes when a patient develops disorders like Alzheimer's or frontotemporal dementia. Conventionally, we measure these alterations by looking for things like spectral slowing or reduced alpha power. And, while these methods has undeniable diagnostic value, they actually have a pretty massive limitation. They treat the EEG reading as one long, uninterrupted, continuous signal. Which brings us nicely to section 2. Continuous waves and rethinking EEG. This perfectly illustrates the stark contrast between the old model and the new approach. The conventional view basically treats the brain's electrical activity like an uninterrupted, continuous radio broadcast, a stationary oscillatory process. But the Ecepj view, it suggests we shouldn't be looking at one continuous wave at all. Instead, it's a series of distinct, transient events. So, think less like a continuous radio hum and more like a sequence of discrete, precise Morse code. Let's move on to section 3, introducing the neurobyte framework, a completely new perspective. Now, the building blocks of this new computational perspective are just fascinating. The Ecepj model proposes that large-scale brain function actually emerges from transient timing events, and they call these neurobytes. Instead of that long, continuous hum we talked about, brain activity is modeled as sequences of short-lived, phase-coordinated integration events. They're basically distinct, rapid bursts of integration. All right, section 4, building a standardized pipeline to see how we actually detect these events. Now, you might be wondering, how does this work outside of theory? Well, this framework is grounded in real, reproducible data. Researchers utilized the Thessaloniki dataset from OpenNeuro, which contains resting state EEG recordings from healthy controls as well as folks with Alzheimer's and FTD. And because this data is so carefully curated and formatted to the brain imaging data structure standard, it serves as the perfect objective benchmark. Let's look under the hood at how they actually hunt for these neurobytes, using Python. First, they import the data, apply a 1 to 30 Hz bandpass filter, and compute a Hilbert envelope before normalizing it all with z-scores. But here is the absolute critical part. They detect candidate neurobytes using a strictly fixed 1.8 standard deviation threshold, locking the event duration between 30 and 500 milliseconds. That means no dataset-specific parameter tweaking, no optimization, just a beautifully standardized, reproducible pipeline. Moving right along to section 5, the fragmentation hypothesis and rethinking spectral slowing. Once processed, this pipeline extracts a highly detailed temporal fingerprint of a patient's brainwaves. It tracks things like event count and density, mean event duration, and the actual intervals between these events, right down to their stability and variation. It essentially maps out the exact rhythm of the brain's Morse code. So, when researchers fed this temporal fingerprint into machine learning models, one metric absolutely dominated the rest: the mean event duration. This specific feature, which measures the exact lifespan of a single neurobyte, turned out to be the most powerful tool for classifying the data. And this leads to a massive paradigm shift. Remember that spectral slowing seen in dementia we mentioned earlier? Well, the Ecepj model hypothesizes this isn't just a loss of power. It's actually the progressive temporal fragmentation of these events. The narrow byte packets are quite literally getting shorter, shattering their temporal organization and destroying that stable, large-scale synchronization across the brain. And finally, section 6, the future of biomarkers and the need for cross-cohort validation. Now, Just to be clear, the NeuroBite framework doesn't throw out conventional findings. Rather, it offers a really vital complementary temporal layer. But right now, it is a scientific hypothesis. Before these timing metrics become true clinical biomarkers, they have to face the ultimate test, prospective validation. Scientists must prove this works across independent datasets, different recording systems, and global laboratories. The foundation is brilliant, but the cross-cohort work is really just beginning.
And if confirmed, this shifts our entire focus toward the incredible, precise timing organization of the brain. And it leaves us with a really profound question. If our very thoughts and our cognition are built on sequences of these transient neurobites, what happens to the human experience when that precise timing is lost? It's a compelling thought, and exactly why following the future of brain biomarkers is so absolutely essential. Thanks for joining me on This Explainer, and keep questioning how we see the brain.